I hope you guys are enjoying your time here. I know I am. My name is Megan Pitt, and I've been given the wonderful honor of introducing these lovely artists. But with that said, not only are these ladies friends of mine, but they're also fellow clay nerds with me at Augusta University in Augusta, Georgia. Shout out to MPO. Not only am I in love with the work that they create, and I'm also fascinated with the process to which they do so, and that's what they're here to tell us about. So without further ado, I provide you Brooke Farmer, Ellen Griffin, and TK Lee.
Hi guys. She made it sound like we're gonna say something really cool, but I'm very sorry, the first bit's gonna be very boring. So, good afternoon. Thank you all for joining us today. We're undergraduate students from Augusta University down in Augusta, Georgia, and hopefully we can get you interested in 3D printing. We'll go over a brief introduction to the whole process and work through a few of the troubleshooting things that we do at back home. But before that, a brief history. As some of you may know, 3D printing has been something of a new fad within the past few years, but what you may not know is that it actually comes from like the 1800s and maybe even further back. In 1860, in the Studio Photosculpture de France, the artist Francois William produced and patented photosculptures, works made by capturing subjects in a series of photos taken in the round, a process that we can recognize in modern 3D processing and scanning. In 1892, J.E. Blanthar proposed three-dimensional topographical maps. The layers were produced from cut sheets of wax, which were stacked separately to produce a positive and a negative, and then a printed paper map would be placed in between to reveal the finished topographical map. These would further be explored by Pereira in 1940 and Zhang in 1964. In 1972, Matsubara of Mitsubishi Motors proposed a process with photo-hardening material, a photopolymer resin, which might sound a lot more familiar to you. The unhardened portion of this would be discarded, and the layers produced would be fixed together to reveal a casting mold, which they would then go to use in the production of car pieces. In 1980s, Charles Hull and technically Alain Lemahout invented stereolithography, SLA, which could reproduce 3D models by exposing a photopolymer liquid to a laser. In 1991, Stratasys, a company you may be familiar with when it purchased MakerBot Industries in 2013, and for its prototyped 3D printed electric car, produced the first fused deposition modeling machine. It uses plastic and an extruder to deposit layers on a print bed. From the 1990s, research and production into 3D printing started to expand exponentially. 1992, DTM produced the first selective laser sintering machine, similar to SLA, but with a powder and laser rather than liquid. 1999, scientists managed to grow organs from patient cells and used 3D printed scaffolds to support them. 2001, Solid Dimension produced the first desktop 3D printer, finally bringing desktop printers into your home. 2002, a 3D printing miniature kidney is produced. 2005, RepRap by Dr. Adrian Bauer produced so that it could one day print its own parts, which it does in 2008 with the RepRap Darwin. In that same year, Stratasys again produces its first biocompatible FDM material. The first 3D prosthetic is produced. 2009, Organovo produced the first 3D printed blood vessel. 2013, Defense Distributed is demanded to remove designs for the world's first 3D printed gun by the State Department Office of Defense Trade Controls Compliance. In 2018, through a lawsuit, Defense Distributed continues its sourcing as DefCAD. 3D printing is still continuing to evolve, albeit maybe not as fast as it had in the earlier 2000s. But there is still development going into it, and it's only more affordable than ever. From 3D printing, we can produce many different things through various mediums, whether it's based in art, medicine, or topics up to more social debate. And these are some examples of the 3D printers. This is the Ultimaker. And you have probably seen this down in the session hall. But I'll get right into it in just a second. This is the Delta model that we go based off of. But enough history. You probably didn't come here for that. Let me speak a little bit more about a few more things before I hand off the baton to my partners. If you looked into machinery at all, you may have noticed several types of 3D printers. And if you're looking to buy one, you will have also noticed the price tag for a few of them. There are several methods to print, and even in those methods are different systems. Material extrusion, photopolymerization, material jettings, binder jetting, powder bed fusion, directed energy deposition, sheet lamination. They're all big words, and I'll speak briefly about all of them, and then we'll get into the ceramics. Photopolymerization differentiates into several different processes like VAT, SLA, DLP, CDLP, etc. In photopolymerization 3D printing, a liquid photopolymer contained in a bank is selectively cured by a heat source, generally a laser. And then the object is created layer by layer. However, nowadays you don't even need to use a laser. In fact, you can use an LCD screen or a digital light processing projector to cure an entire layer of resin at once. Another differentiation comes from the printing of the bed, printing itself, where the bed is actually lowered into the vat of resin to slowly build each layer. So it prints upside down, or printing otherwise, so your finished product is upright. Sheet laminations consist of superpositioning several layers of material composed of foil to manufacture an object. And this foil can be paper, wood, or in this case, developed into the metal cutting as well. Each foil is cut to shape with a knife or laser in order to fit the object's cross-section. The latest developments of sheet lamination has made possible the use of carbon fiber sheets. In paper-based laminated object manufacturing, the paper material is taken from standard copy paper. First, it goes to be printed through a standard 2D inkjet printer, and then from there, it's stacked into the 3D printer. Glue is applied, and each layer is put on. Each sheet is then cut with a knife or a laser, and then you can pull away the excess paper, and you have your finished product, which can be finished like normal wood or any other composite. Powdered bed fusion and directed energy deposition are both options to print in metal in a sintering process. You might know that in Brussels, they're currently 3D printing a bridge that can be used. Amsterdam. Excuse me. Material jetting, 3D printing manufacturing techniques are often used and compared to the 2D ink jetting process. It uses photopolymers, metals, or wax to solidify when exposed to light or heat. This is generally so that you can print in multiple materials at once. Specifically, it dispenses a photopolymer from hundreds of tiny nozzles and a print head to build a part layer by layer. This allows material jetting operations to deposit build material in a rapid line-wise fashion, which can be compared to other point-wise deposition technologies that follow a path to complete the cross-section area of a layer, also called a slice. And we'll go into more nomenclature with Ellen and Brooke. As the droplets are deposited to the build platform, they are directly cured and solidified using UV light. Material jetting processes require support, which is often 3D printed simultaneously during the build from a dissolvable material. An example being from the latest from Stratasys, the J750 can print multiple materials of varying firmness in thousands of colors in one session. Material extrusion is the most common method and one most ceramic artists use. The typical model you'll see is built on a Cartesian system with arms that move along an x-axis and a y-axis and a bed that moves along the z-axis. Material extrusion prints layers out of a semi-liquid material usually a thermoplastic of some sort that is heated to its temporary viscous state. Our printer is based off the Delta system, which you can see here, and uses 3 arms. These arms move up and down a chute via bands and a motor, either independently or in conjunction with each other to direct the nozzle as needed. This model in particular is very handy for interest in taller vessels. Most 3D printers are restricted by their size, but Delta printers are convenient in a way that you are only restricted by the bars and your bands. So if you wanted to build taller, you could always find better accessories. There are expensive options in each system, but for our department, we were fortunate enough to invite Brian Sibes to our ceramic studio to offer a demonstration and produce our own 3D printer, which we have endearingly named Pierre. Once you have a 3D printer, you will need to consider your supplies. Oops, sorry. Well, this is actually a website that you can go to find various 3D printers that they have the build and they'll have the circuitry, the programming that you need to install to your Arduino or the like. And you can find them all online. And this was supposed to be a short video that shows you exactly where to click and whatnot. But you can find the Delta model here as well. Once you have a 3D printer, you need to consider your supplies. Your machinery affects what materials you can use and what means you can use them with. A higher-end 3D printer can print directly from a Pug Mill or use the pressure from a mechanical arm to extrude clay. Some can even extrude concrete to build houses. As you know, they are currently building temporary housing out with enormous 3D printers. For us, however, Pierre is endearingly small, but what he can't hold up with sheer power, he makes up for in speed, which we'll get into later. As a Delta model, Pierre's lightweight frame, motors, and band mean that our clay must be soft and our extruders light. And you can take a look at some of our tubes, and you can come up after the talk to see just how light these are. From here on, I'll speak even less, I promise. I need to leave a couple things for Brooke and Ellen. Oops. There are various resources to produce the 3D models with which to print. You can directly replicate objects through photography, or you can even make your own models completely digitally through various programs. From there, the objects need to be broken down into a language that your 3D printer can understand. And Ellen will go into the actual terminology and the language. As ceramic artists, we have an amazing range of flexibility in our medium. You can produce precise and clean finished pieces or produce amazingly organized chaos. There's precision to 3D printing, and then there's your hand as an artist. Whether you work directly with your art, whether you directly affect your work before or after or even during the print. Brian Sibes, for example, fuses his work with slip-casted objects to produce beautiful finished pieces. You can experiment and push your material to its limits, and then some. For instance, we had a special situation in our summer research back in 2018, which led to this talk. At some point after troubleshooting, we finally decided we were ready to add color to our clay. We mixed several mason stains with our B-mix and packed our tubes to print. And then, of course, we asked ourselves, well, can we print with 2 colors? We knew at the time that Lutum had recently prototyped a dual clay nozzle for their clay printers, but it wasn't quite what we wanted, and definitely not within our budget. So we called another artist for his insight. He had recently given an artist talk at our school and given students more inspiration for 3D printing. However, when we spoke with him in depth over the phone and explained that we wanted to print Crest toothpaste, our leads fell short. It just wasn't done. And it couldn't be done as far as we knew. So I said, fuck it, and we did it anyway. We brainstormed over how we might Frankenstein our supplies to extrude 2 colors at once, but there wasn't a feasible way for us to do it without compromising weight or stability of our medium. In the end, I just packed it by hand. And as far as our research goes, we were the first to print multiple colors of clay at the same time, as shown. And you can, after the talk, come up to get a better look at them. You can get beautiful, illusionistic color changes with, your knowledge of color theory. And if you get the chance to come up here and just pick one up and just. But thank you. Let me pass the baton off to Ellen.
How are y'all today? My name is Ellen. I'm going to briefly go over the computer side of ceramic 3D printing. So I'm going to go over a couple softwares that we use and a couple tips and tricks of troubleshooting that we ended up using. We started with no experience in either 3D printing or in computer programs to do so in. So we sort of like what we learned over those 3 months. But before we go into talking about creating files, we need to talk about what files can't be, sort of the limits of at least our system of ceramic 3D printing. Some of the things are you don't want your piece to be too top heavy. The wet ceramic has the consistency of about a facial cream when it's mixed up properly. And that just simply cannot support its weight if it has more material on top than on the bottom. Another thing you want to try to avoid is real sharp angles in your piece. It just simply doesn't have the strength to support the rest of the piece if it has these real sharp angles and will simply collapse. Some of the CAD programs we end up using are Mesh Mixer, Rhinoceros, and Fusion 360. A CAD program is simply computer-aided design. It is a program that gives you a virtual space to create these digital objects, which can then be converted into a type of file called G-code, which is then put into a 3D printer to print. Mesh Mixer is what we started with. It's a sort of your general all-purpose CAD program. We found it to not be very beginner-friendly, however. It's more used for people who know what they're doing. So for people who have no CAD experience like ourselves, it's a little difficult to navigate. In a similar vein, Rhinoceros, which we also used. It's a very powerful and very precise program. It's actually used in industry for creating the hulls of cargo ships. So it can get very precise and very accurate in its modeling. One program that we did end up using is Fusion 360, which is we found to be very beginner-friendly and very intuitive. It allows for you to figure out what you're trying to do without all the years of experience with these programs. It comes with its own tutorial series, and it has very good resources online. One YouTuber I watched the tutorial series for was called Maker's Muse, and I would highly recommend both that and Fusion 360's own tutorial series. Another program that we used is called PotterDraw. It's made specifically for ceramic 3D printing. It's made specifically for making vessels that are then can be used for 3D printing. And I'm going to briefly go over how to make files in PotterDraw just to show you how user-friendly it is. So when you open PotterDraw, you're going to start with this basic cylinder here, with this crazy texture on it that can be changed later if that's too distracting for you. You can see you start with a basic cylinder, and to the left you're going to see what's called a spline, and to the right you're going to see your properties. Now, properties are different values that you can put in a number value to then edit your piece, and we'll go more into that in a second. The first thing you want to do is control your spline to the left. And that is simply a line or a curve that your rest of your piece is going to follow. This is going to give you your rough shape of your piece. So you can see there I made a curve, and that's what the whole wall, the rest of that piece follows. You can add nodules to give you a couple more bumps in there, or even change the distance of your base, all with the control of that spline. It's one of the quickest ways to get a rough idea of what you want with the piece. From there, you're going to go over to the right to Properties, And from there, you can input number values into each of these different properties to edit your piece. So you can see here, I went through and added 5 sides, and it gives you 5 sides with a pentagram shape. Then I went down and added a twist of 0.2 that just simply rotates the top and bottom of your piece to give you that twist through it. And then from there, I added 5 ripples to it. It gives it those bumps on the side. What we have found, however, to be careful of is some of the things like the ripples have a depth option. So if you go and you put 5 ripples on the default, nothing's going to show up. You're going to want to go down to your depth and give it a space for it to go out of your piece. So at a depth of 0, you get a flat line. A depth of like 15, you'll be way over here. So if you're ever editing in PotterDraw and nothing's happening, make sure your depth is not set to 0. There are some things that you want to try to avoid within PotterDraw, specifically scallops, the whole section in there. You just want to pretty much avoid those, and also some of the motifs, which are a decorative element to some of the properties. These tend to change the thickness of your wall unevenly through your piece. So you can see here on the top of the bump and on the inside of that trough is thicker than the walls connecting them. And that's going to cause you issues down the road when you're trying to print your piece. So it's just good things to keep in mind and pretty much just avoid. But that being said, you can get really creative with these properties. We actually printed this piece here and called it Popcorn Shirt for the obvious reference of those crazy shirts that look just like that. But we were actually able to print this no problem the first time. So you've made your file, you've made your object, now you're ready to print it. Well, there's one more step you have to go through before you actually get to the printer. So you have your CAD program, you're also going to need a slicer program. The program that we used is conveniently called Slicer with a 3 instead of an E. A slicer program simply takes that file and cuts it into rings or slices for the printer to follow with each path that it goes. Slicer programs will convert it into G-code, like I was talking about earlier, which is simply a series of coordinates that the printer follows. I actually have an example of G-code to the side, so you can see it's just a X, Y, Z coordinates and a specific time the printer is supposed to be there. So I'm actually going to walk you through Slicer a little bit. It's going to get a little technical because we're having trouble with Slicer itself. It tends to be a little finicky. It's a free program, so you really get what you pay for. But it's definitely workable and useful to use. As you open up Slicer here, you can see you have your file in the middle and a representation of the platter that you're printing on to sort of give you a sense of scale. It has measurements down the left-hand corner that I believe are in millimeters. So a thing to keep in mind when you're looking at that. It has 3 different views down at the bottom right, 3D, 2D, layer and preview, I believe. 3D is what you see here. It always looks perfect. You'll never see a problem with it. 2D is just it's like the profile of the bottom of your piece. It's not very useful for anything. Layer will show you a line, like a drawn line of the path the printer is going to follow on that specific layer, and you can tend to do a little bit of troubleshooting with it. The most useful is the preview, which will actually show you a representation of the path the printer is going to take, and we'll get to that in a minute. But we were having trouble with the printer, with the resolution and the speed, and we found that going through some of the settings within Slicer helped that, so we're going to go through that a little bit. The first drop-down you're going to find is called Layers and Perimeters. This is how you're going to tell the printer how high each layer is going to be and how many walls you want it to have. The layer height we set at 0.88 or 0.8 millimeters, and that's determined by the size of your nozzle. So our nozzle was about 8 millimeters wide, and we set it to that to give it that layer height. Perimeter is at 2. We generally try to print with our walls too thick. That simply means it's going to print one layer and it's going to print another layer right next to it. So you have like one wall and another wall printed in your piece. I personally like to do it with 2 because that just gives you very thin walls, but also a little bit of a buffer if you have a change in clay consistency or an air bubble. It gives it another chance for that clay to stick to the previous layer. But that can be changed at will. You can print at 1 or all the way up to 5. It's a personal preference. Underneath that, you'll find what's called vase mode, which takes away that the perimeters and only allows you to print 1, but it takes out what's called a zipper. The zipper is a mark left behind by the printer as it bumps up to the next layer. It'll simply leave it looks like a zipper on your piece, a little bit thicker area. And vase mode just simply spirals around, slowly increasing what's called the X value, which is just how high your nozzle is. So it gives you a smooth, clean, zipper-free piece, but it limits you to 1 perimeter. Horizontal shells help you control your bottom layer. We found that a top of 1, bottom of 2 gives us a 3 thick bottom on our pieces. That just gives you a nice solid bottom, and it prevents cracking from something too thin, and allows for even drying. Seam position, we usually have it at nearest. That just allows that seam to be in one area instead of jumping around as it sees fit. And then external first, if you're printing in multiple perimeters, that just allows for that outside one to be printed first before it goes to the inside ones, and it gives you a cleaner print, we found. Next one is called Infill. Infill in the 3D printing world is a support material that's printed at the same time to support either your walls or to allow for you to print over an open space. It's a lattice work that's put on the inside of pieces. So for vessels, it's not very useful. However, you're printing like a 3D scan of a face, and you have the nose on the top. If you try to print that without infill, it'll just collapse in, unable to support its own weight. But with infill, you're able to give it the support it needs to complete the print. Another thing we found with vessels is that the infill controls the Padam on the bottom of your vessel. And from there, you can control what you see when you pick up the piece. So the path the printer takes is going to be recorded on the bottom of your piece, and from there you can actually set it to curves or concentric or a geometric pattern. There's different things you can do with that. The next setting you'll find is not very helpful. It's called Brim Skirt. It's just not. It controls, you see that green ring on the picture? That is the skirt. It is simply the first path the printer is going to take. It's going to trace an outline of your piece before it starts on the piece itself. We found that it's helpful for testing if your settings are correct. It's sort of like a little bit of a test before your actual piece. The most important ones that we edited is the speed settings. We were having trouble with prints taking 4, 5, 6 hours depending on the size of the piece. And for summer research, this wasn't viable. But we were able to get it down to print maybe 30, 45 minutes depending on the size. So we bumped up all the speeds to 20, but kept the top solid infill at 15. The top solid infill is part of our bottoms of our pieces, and going slower just allows for a little bit more clay to be deposited, giving you a thicker bottom. We set all non-print speeds to 50, and that's just the traveling speed from one part of your piece to the other when it's not actually printing. There's a traveling speed to leave as little clay behind as possible. And the modifiers, all we changed was first layer 15. That again just gives that bottom layer a little bit more clay. And then at the auto speed, we set to 80. I believe that is default. A couple other things that we found useful. Having first layer at 200%, overlap 15, all others at default. These are just little tweaks. I don't remember exactly what they control though. And the last setting we're going to go over, there's just a couple interesting things on it. It's what's called the print settings. This is where you're going to control what's called your Z offset and your G-code flavor. Z offset is simply where the printer starts in space. So it's the Z or the up and down value of your printer. And with the Z offset, you can set it to start 5 layers above the platter. And start printing there and let the clay like noodle out before it catches back up. Sort of this chaos to order is some design choice you can make. And also helpful for controlling your alignment with the bat itself. So you can, if you're printing off of the bat to start and it's not what you want, you can take that Z offset and move it down to find your base again. Another thing to find here is your G-code flavor. It's just simply what kind of brain does your 3D printer have. It has a couple different options in that. So last thing, we're going to go over a couple different troubleshooting while you're still in your programs. As you can see here, we have your three different views, your 3D, your layer, and your preview. As you can see, the 3D looks perfectly fine. You'll never see a problem with it. The layer, you can start seeing a problem where it's tracing those lines, and then over in preview, you can see where the problem is starting. So you see that little bump or distortion on that picture? That is actually where the side of the perimeters are uneven. This is what typically happens with that scallop setting. As you can see in the layer, there's two thick walls in the middle, and then it goes to a one thick wall on those corners. So essentially what the printer is going to do is it's going to trace a circle for those two thick, and then a line for that one thick. And the circle and the line just never end up joining and will actually be torn apart during printing. So for this, you can sometimes fix it with a scale. You can scale the piece up, scale it down. I generally start with a 50% either way just to see what that does to the piece. And usually you can get it to a nice balance where you can get even numbers of perimeters. Another problem we're having is walls just not being there at all, not being printed at all during printing. And as you can see in 3D, it looks just fine. But over in the preview, you can see where those walls are just not going to be there. And what's happening there is that the walls are too thin for it to even put one perimeter down. You're going to have to go back into your CAD programs and increase the thickness of that wall. Sometimes you can get it through scaling, but generally you just have to go back and bump up your walls again. And for a file to be successful, these are the views you're going to want to see. Of course, 3D looks fine. Layers are good. You can see those solid lines all the way through. And your preview is perfect. You can see all the layers lining up really nicely. So once you have this, you've gone through troubleshooting, you're actually ready to get into the physical side of 3D printing, which Brooke is going to come over.
Yep. As Ellen has said, I will be going over more of the physical part of printing. To begin with, there's like different things. You obviously running the print, problem solving, and what problems can occur. But before you even start with that, you are going to have to prep your clay. The way that we prep our clay is like once we get it out of the box, we take it into, of course, clean kitty litter box. We fill it about 2/3 of the way, and we poke holes into the clay so water can seep in a lot faster. And then if you want to add in mason stains, which of course we do, and then some of the times we didn't, you can mix it into like 2 different ways that we do, or a different way that you would prefer. I personally love doing it by hand. I have a bucket already with my clay prepared in it, and I start mixing it in, or you can fold it in with a spatula. And then once your clay is prepared and ready, you will start packing your tube. Our tubes are pretty easy to pack. We have a spatula that we have cut to be able to fit inside of it, so we don't have too much clay falling out as we're packing it. As we've mentioned before, that we do did dual colors, splitting it in half. So one way that we didn't contaminate the different colors, we would separate them and make sure that we have 2 different spatulas to keep it very separate. And then once the tube is packed, we wrap it up with plumber's tape to make sure that it is sealed, and we would have less of a chance of leakage when printing. When it comes to printing, there are different variables that go into it, such as moisture of clay, pressure of air, and speed. They all go hand in hand with each other. So with the moisture of clay, we found that it needs to have a lot of water added into it, even after we have soaked it. That way there's not a lot of need for air pressure, so it can be pushed out. We've experimented with a little bit of clay. We usually use about 2 pounds to begin with, as we are prepping with our clay. And we usually use about 2 cups or 16 fluid ounces of water to get the consistency of the facial cream, as Ellen had mentioned, because that is the consistency that we desire to print. I personally have used about half that amount of water to print with, but I had to increase the air pressure much higher than we prefer to print at. When it comes to the air pressure, we usually tend to stay between 40 to 60 psi, but I have gone up to 80 psi with the half amount of water. Printing at that high of a pressure means it could cause us a lot of problems in the long run, and I'll go over that as well. Our goal is usually to print about 40 psi, making sure that our clay is at the right consistency and we don't have any problems as the clay is being pushed out through the tube. When it does come to air pressure, though, we have had troubles making sure that we don't have any leakage as it's being pushed out through the tubes. This is an example of one of the tubes that we use. We have this end connected to another one, connected to our pneumatic system. And it took me about a month, but I finally finessed a way that once they're connected, because there is a small gap in between them to reduce the amount of leakage, it takes 2 layers of plumber's tape, 2 layers of electrical tape, 1 layer of paper towel, and then 1 more layer of plumbers and 1 more layer of electrical, and then we put a clamp on top of it. I have gone through many clamps because I've constantly had to keep up with the maintenance to make sure that we don't have leakage, and if we do, I just fix it again. Speed can also affect the outcome as well. I have made speed testers, as you can see here, that range from 140 to 220 and 300 to help us understand the effects speed has. Our main conclusion that we had to gather after doing these tests was that the higher the speed you will see less of the resolution in the print itself. Speed can also affect the pressure as well. If you were to print at a higher speed, you would have to increase your air pressure as well to match the speed so you don't lose the form of the work. And then up here, this is the screen that we normally see. All the way to the left would be FR, which we call flow rate. That is usually the number that we will look at for so we can see what speed we are printing at. Like I said, things can go wrong. As we print, we usually expect something to go wrong, being that it's not always perfect. Our clay can be drier in different spots in the tube as that was packed. There can be air pockets that we didn't see that can blow a hole into it, or there can be too much weight on one side of the work. We've come up with different ways to fix these problems, but the main solution that we have is usually just increasing the air pressure. That way, if to fix a hole, we just turn it up real quick and turn it right back down so it'll fill up that spot, or we just increase the pressure so it can continuously catch up with itself. And also we had discovered that because our pieces had been getting stuck to the base that we were using, we had to find a new solution to resolve that, and we had decided to use wax paper. We usually leave it on about 24 hours so it can dry. Once those 24 hours are over, we're able to peel it up and we won't have a crack or the base of the form doesn't move on. These are some other pieces that we have done in the past, being that you can see what happens if the clay goes off on its own. The one in the top left is actually way too much water has been added into the clay itself. And so even having at a very low amount of air pressure, it just would seep out. The one on the bottom left, what had happened had the pressure was too high, so it's just completely just extruding out with nothing to fully grasp onto. And the one on the far right is where, thank you, the angle was too steep, so on the very top, they would fall in on itself. I have been working on a series of works for a show that's coming up in April. I've continued my own research outside of this, but still taking in on everything that I know now. They're very simple forms that I've made through Potter Draw. So I've been working off of triangles, square, and circle. The clay that I work with is very moist, using much more water. I have added about half a cup more water than the 2 cups that we usually use. The pressure varies between like 40 to 40 psi, and I work at a set speed of 120. I like to manipulate my pieces. So as the pieces are printing, I allow them to continuously print until they're like 20% done, and then I would move them from their spot after already marking where the original location was, let it print some more, and then I would bring it right back. That way, as it moves from back and forth, it is falling upon itself and allowing it at the same time then catching up. I thank y'all for coming out today. If you have any questions, there is a mic up in the middle. Feel free to ask.
Just what are some ways in which you see that the technology around clay 3D printing needs to further develop or be continually pushed?
You got an answer? Here you go.
So I don't know if you know, there are more than just the extrusion for ceramic printing. For factories, they'll actually print through a powder bed, and they'll print a layer or have it cured with a liquid base or something like it, and then it'll put another powdered layer and then keep doing it in that manner. And that's how they mass produce their prototypes. I think the biggest problem with 3D printing right now is the connection between prepared material and printing process. But a lot of more advanced 3D printers don't have that problem because they have things like Pug Mills or the like that have powerful arms that can extrude clay. So like this one is actually forcibly extruded by an arm, so it's much more controlled. Where we have problems because we work with a pneumatic air system, so if there's a hiccup in the air, or if we have a small air pocket, it'll cause big problems.
And this kind of system that's being sort of like pushed by this arm, it's less suitable for like individual, like home use, or rather individual use?
I would, it's just a little bit, it's a higher price range, is unfortunately what it comes down to.
Not as accessible.
It's much more reliable, and you can tell you can pack more clay into it as well, so you can make for bigger, wider, taller pieces. She actually printed a piece that was about 1.5 feet tall, and she had to go through, I think, 6 tubes?
3 tubes.
3 tubes.
No, 4 tubes.
4 full tubes. So.
Is there a kit like this in the open build that would build like a ceramics? Like a 3D printer?
I think now they have things like this where, and you can also buy these as well, because it is ultimately a mini Pug Mill, and so I think I have seen something similar to it.
Thank you.
Are you going to have these files available?
If you would like anything from like, especially when Ellen went over like the nomenclature and stuff, if you'd like to get a copy, you can just give us your email and we'll send it to you.
That would be awesome, because I'm getting a printer and I don't know what I'm doing.
This is definitely the tutorial, this is like the tutorial YouTube video before you go into like, this is how you print this thing.
That's what I need.
Yeah.
Okay. And then my other question is, how much shrinkage do you have? Because you're adding so much more water.
So, surprisingly, the shrinkage is about standard to,
Really?
yeah, we use, for our clay, we use B-mix with no grog, and it does shrink a little bit more, but it's still close to that 33%.
So what firing temperature? Sorry, I keep asking questions.
So
what firing temperature?
we have
did you
taken ours up to cone 10.
10. Awesome.
Yeah.
Thank you.
No problem.
So I have a question. My limited knowledge of 3D printing is that it's a very kind of precision-driven kind of concept, and I've kind of noticed that you seem to lean more towards distortion with your printing. I was wondering if you could speak to that.
I've usually been the one to very much experiment the entire time we were doing research. If something would go wrong.
She got yelled at a lot.
Yes, I would get yelled at a lot by them. Every time something messed up, I'm like, no, let it continue printing. Don't restart. I want to see where it goes. So after having the fun of like being loose and letting it just go, that's how I developed where the pieces I have now. So I'm able to understand that I can cause the distortion as well as it just messing up on itself.
Can you help me understand how you're creating that distortion, I guess? Like how is your hand involved in the process that helps manipulate and create distortion? I guess I'm very interested in how you're doing that.
With the pieces that I'm currently working on, I am moving the form from its original spot to a different spot, just back and forth. That way, it has different layers popped on top of each other.
Thank you.
Uh-huh.